AI is starting to get more efficient in places most teams still treat as fixed: how data is mixed, how tokens are committed, and how capacity is spread across depth. That matters because the next round of gains may come less from scaling everything up and more from learning where the model actually spends its budget. This week's results point to a broader shift toward measuring hidden behavior instead of trusting surface assumptions. Keep watching, because the surprises are in the details. Let's explore the first paper: Causal Mixed Data Mixture as Causal Inference for Language Model Training. Causal Mix, developed by researchers from Tsinghua University, Ant Group, and Renmin University of China, reframes supervised fine-tuning data mixture search as a causal inference problem rather than a static regression over past runs. The method uses 512 proxy trainings of Quen2, 5 to 0, 5B on 100K, example mixtures from Tulu, 3, SFT mixture, extracts state covariates from Open Data Arena, scored data 2603 using normalized, loss, HES, and writing style, and fits a causal forest DML model with light GBM nuisance predictors to estimate state-conditioned marginal returns on log mixture weights. On the main Tulu 3 benchmark suite, Causal Mix A reaches 33.94 AVG dev at 800K data with Quen2, 5 to 0, 5B, while Causal Mix S reaches 62.28 AVG dev on Quen2, 57B at the same 800K scale, both exceeding prior data mixing baselines such as RegMix, Duremi, ODM, and DMO in the reported settings. The framework also transfers to an unseen long cotangent style setup on AM, Thinking, V1, Distilled, Code, and Math, with Quen3, 4B, Causal Mix. Achieves 66.66 average score, ahead of the 64.74 best grid baseline. An ablation shows that removing covariates or DML orthogonalization degrades performance, confirming that the gain comes from state-conditioned causal estimation rather than ordinary mixture regression. The paper also reports a closed-form simplex policy: allocate only to domains with positive estimated causal effect, normalized by ReLU-style weighting. Let's explore the second paper: neither parallel nor sequential how DiffusionGemma actually commits tokens. This DeepMind Google study audits the shipped open weights checkpoint Google DiffusionGemma 26B A4B IT, a masked discrete diffusion mixture of experts model built on Gemma 4 by instrumenting its entropy-bound sampler. Accept, canvas, commit path, rather than retraining anything, across a 686 prompt probe suite spanning GSM 8K, human eval, MBPP, factual recall, open-ended instructions, and constrained JSON. The authors find that DiffusionGemma is neither truly parallel nor purely sequential. Content token commit order shows a moderate left-to-right bias with tie-aware Kendall Taub from 0.43 to 0.604, but it remains well below a block sequential control near 0.94, 0.96, and commit batches are large at roughly 1326 tokens per accept call, with same call tie rates up to 0.72. The headline claim is that granularity matters. Block Taub rises smoothly as analysis bins grow from 4 to 64, with no special jump at 16, so 16 is just an analyst choice, not an architectural boundary. Behavior is also regime dependent, with constrained JSON essentially order independent at Taub equals 0.044, while commit confidence is meaningful only in some tasks. On GSM 8K, negative entropy predicts correctness with AUROC 0.749, but on factual recall, AUROC falls to 0.471. Despite a 4.8 step budget, generations finish in a small late burst at entropy 0.002, 0.012 nats, well below the 0.1 bound, and overall accuracy stays comparable to the autoregressive sibling Gemma 426B, A4B it on the scorable regimes. Let's explore the third paper: tapered language models. Tapered language models from Mila and Cornell University with Aaron Corville challenge the default assumption that every layer in a language model should get the same parameter budget. The paper shows that when MLP width is redistributed across depth under a fixed parameter and flop budget, front-loading capacity consistently beats uniform allocation. On a 440M transformer, a cosine taper reaches 14.44 validation perplexity versus 16.28 for the uniform baseline, while the reverse, Backloaded allocation rises to 17.29, using the best cosine schedule with a 1, 5 over 0, 5 start to end width ratio. The authors report gains across 4 architectures: Transformer, Gated Attention, Hope Attention, and Titans at 760M and 1.3b parameters. For example, average common sense accuracy improves from 52.25 to 52.84 on Transformer++ at 760M, and from 56.05 to 56.38 at 13b, with perplexity improving on Wikitext and Lambda in nearly all comparisons. The mechanism is supported by layer-wise cosine similarity analysis on pre-trained GPT-2 checkpoints from 124M to 15B parameters, where both full block and MLP updates become more aligned with the residual stream as depth increases, implying that later MLPs write less novel information. The key technical takeaway is that depth-aware capacity allocation is a free architectural lever. Tapering MLP width improves language modeling, common sense reasoning, and long context retrieval without increasing parameters or compute. That's a wrap on today's AI paper highlights. Thanks for watching.